At this point in the game, you know so much about covalent bonding. We know how to draw the electron dot structures. We know about the three-dimensional shapes that we can develop using the VSEPR theory, looking at the groups of electrons around the central atom and predicting how they would repel and give us certain angles and three-dimensional shapes. We also know about bond polarity. And so now it's time to kind of put all three things together and eventually determine the polarity of not just a singular bond, but the polarity of an entire molecule. And whenever we use this word polar, it refers to regions of charge. And often you'll see this Greek symbol, this delta, and it's kind of either going to give you this, either something like this, partially positive or partially negative. So that Greek symbol delta just means partial. We can either say partial positive or partial negative. We use that in describing the way electrons are shared between two different nonmetals. So for example, if I had hydrogen bonded to fluorine, well, I can just look at the periodic table and tell you that based on the position of hydrogen and fluorine, I know fluorine will have a higher electronegativity. That's the ability to attract and pull electrons in toward yourself. Well, fluorine is a really small atom, so there's lots of attraction between the nucleus and its own electrons, which then also can create attraction for neighboring electrons. I also know that fluorine has 7 valence electrons and really wants 8. If he gets that 8th electron, he fills his octet, which then makes the fluorine atom really stable. Fluorine has the highest electronegativity of all elements on the periodic table. And as I move toward fluorine, electronegativity increases. And so if I know that fluorine has a higher electronegativity than hydrogen, it just means that the electrons are going to be pulled toward the fluorine. So they'll be shared, but not shared equally. And when we draw Lewis dot structures, we might draw something that looks like this, where there's 1 electron and then 7 valence electrons on my fluorine. I can connect the dots, and often that's maybe how we draw our dot structure. But knowing now that fluorine has a higher electronegativity, that pair of electrons is not really shared equally between the hydrogen and the fluorine. It'll be pulled closer to the fluorine. And so in reality, maybe it would look kind of like this, where that electron pair is closer to the fluorine. It's not really right in the middle of the two atoms. And we can show that a whole bunch of different ways. So one option is with an arrow, and the arrow will point toward the atom with a higher electronegativity. The electrons are always pulled in the direction of the atom with a higher electronegativity, which in this case is fluorine. So we could use an arrow. We could use those partial positive and partial negative symbols to show that the fluorine end of the molecule is going to be a little bit negative, and the hydrogen end that's going to be lacking the electrons is a little bit positive. And electrons are negative, so if they're being pulled toward fluorine, then that makes the fluorine end a little negatively charged. You might also see a model that looks like this. It's called an electrostatic model, where the red color is supposed to show a region of high electron density, which is the fluorine. The electrons are going to be pulled closer to the fluorine, so that makes it a little bit negative. That's where the electrons tend to hang out, which then means the hydrogen is lacking the electrons, and so that end will be a little bit positive. All three are fantastic ways of showing that this is a polar bond. Polar, again, meaning that there's going to be a region of charge. That we can also think about not only polar bonds, but also polar or non-polar molecules. And that's where everything comes full circle. That this is the polarity of the bond. And obviously, if there's only one bond in the molecule, if that one bond is a polar bond, well, then you've got regions of charge in your molecule. And we could also say it's a polar molecule, meaning that the whole molecule has regions of charge. Now, if I had a nonpolar molecule, something really simple like hydrogen bonded to hydrogen. Well, obviously, if I have the same atom bonded to itself, it's going to share the electrons the same, and the electrons then are not being pulled closer to one hydrogen or the other. They'll be shared equally. And that does not create regions of charge, which then means there's no partial positives or no partial negatives. And we'd say it's a nonpolar bond. And since it's the only bond in the molecule, we can also say it's a nonpolar molecule. No regions of charge. So if you have a very simple molecule that only has one bond, if that one bond is a polar bond, it's a polar molecule. If that one bond is a nonpolar bond, then it's a nonpolar molecule. But most molecules have more than one bond. So that's what we have to take into consideration, all factors. The polarity of a molecule is determined by not only the polarity of the bonds, but also by the geometry of the molecule. So we have to take all things into consideration. What kind of bonds do we have, and how are those bonds arranged around the central atom? So I want to jump ahead a little bit and actually look at nonpolar molecules first. So a nonpolar molecule means that there will not be a region of charge, no substantial region of charge. Okay, now that might mean that it's nonpolar bonds, but it might also mean that the bonds are polar, but they're arranged in a way that they cancel each other out. And a great example is carbon dioxide. If you draw the dot structure for carbon dioxide, you'll end up with two double bonds between the carbon and each oxygen. Now, if I look at a singular carbon-oxygen bond, I don't care if it's a single bond, double bond, triple bond. If I look at the periodic table and I find carbon and oxygen, well, oxygen is right next to fluorine, so it's got a couple extra protons, a couple extra electrons, so there's a little stronger attraction. It's already got 6 valence electrons, so it's a little bit closer to that octet. Oxygen will have a higher electronegativity compared to carbon. So in a singular carbon-oxygen bond, we have a pull for the electrons to be held closer to the oxygen end of the molecule, or the oxygen end of the bond, I should say. It is a polar bond. The bond between carbon and oxygen is polar. I have two different nonmetals, so they're going to have different electronegativities. The electrons are pulled toward the atom with a higher electronegativity. So that's why they've got these arrows pointing out toward the oxygen. The electrons will be drawn out toward the oxygen and toward the oxygen. But think of this as a tug of war, where maybe like the flag is the carbon atom and all the electrons around carbon. That represents the flag. And then I've got two oxygen. They're pulling in opposite directions, but they're pulling with the same force. It's the same atom, right? It's two oxygen atoms, so of course they're both going to pull with the same force. And the key now is that they're arranged at perfect 180-degree angles. So it's a perfect tug of war where each person is pulling in opposite directions with the exact same force. So picture this in your mind. Does the flag move? If I've got two people pulling opposite directions with the exact same force, the flag doesn't move, right? The flag doesn't move at all. And so even though each individual bond is polar, they're arranged in a way so that they cancel each other out due to the geometry, due to the bond angles. They're at equal angles around the center atom. So they kind of cancel each other out. And the molecule really does not have a substantial region of charge. And we might expect that there would be like, a partial negative on the oxygen and a positive on the carbon. And that really doesn't happen. That These little poles cancel each other out. The molecule is symmetrical, so the poles are happening at equal angles. And then because of this shape, we say the molecule is overall nonpolar. Polar bonds arranged at equal angles will cancel each other out. And then it leaves you with an overall nonpolar molecule. Everything is symmetrical at equal angles, equal poles, nonpolar molecule. Okay, now watch this. So the shape of this carbon dioxide molecule is linear, right? So if I just kind of sketch a linear structure. And now remember, linear can be single bonds, double bonds, triple bonds. We don't care as long as there's only 2 regions of electrons on the central atom. That's linear. Linear molecules have an equal arrangement around the center. So as long as I have equal poles, the structure gives me equal angles. So I could be pulling out this way, but if I have an equal pull in the opposite direction, it cancels. And that leaves me then with a nonpolar molecule. Even though the bonds individually might be a little polar, if they cancel each other out due to their arrangement around the center, you could be left with a nonpolar molecule. Check out this shape. What about the trigonal planar? 1, 2, 3. I should put in 2. Like, these are beautiful 180-degree angles. Remember this guy where you've got the perfect 120s? It's a perfect flat triangle. 120-degree angles. This is my trigonal planar structure. The same thing can happen. That I might have a polar bond, but watch the way these bonds are arranged. So I could have, let's go yellow. I could have a pull here, I could have a pull here, and a pull here. But it's like a 3-person tug of war now. Where as long as the atoms on the outside, the 3 atoms on the outside, as long as they're the same, well, then they're going to have the same electronegativity. And they're going to pull to the same extent. It's like a 3-person tug of war, where again, the flag is like the central atom and all the electrons around the central atom. But now I've got 3 people pulling at perfectly equal angles, 120-degree angles. And again, these 3 people are all pulling with the exact same force. They cancel. Those little pulls cancel. You could have pulls because the bonds are polar. The electronegativities are different between the atoms and the bonds. But if those poles are arranged at equal angles, they'll cancel. And then it leaves you with no substantial region of charge. We'd call it a nonpolar molecule. Check out this one too, the tetrahedron. I'll try drawing it in 3 dimensions, because this one is not flat. 1, 2, 3. Can you see my little rocket ship? Here's my little tetrahedron. Here's my little tetrahedral rocket ship, where around the center I can get better than 90-degree angles. All these angles, because again, it's 3-dimensional, so they're really equal. They're all 109.5 degrees. You don't have to have that memorized. Just know that they're not 90. I can do better than 90 degrees if I go in 3 dimensions around the central atom. I want those electron pairs to be as far apart as possible. But now, as long as the electron groups are the same, I could have a little pull, and a little pull, and a little pull, and a little pull. If I have equal pulls at equal angles, they'll cancel. And that leaves me with an overall nonpolar molecule. These 3 shapes are the 3 shapes that are often nonpolar molecules. Because they're the three shapes that have equal arrangements of atoms around the outside. The linear, trigonal, planar, and tetrahedron have perfectly equal angles between all the atoms around the center. So as long as you have equal poles, the shape of these molecules will give you the equal angles. And the polar bonds will then cancel, and you're left with an overall non-polar molecule.